Let's talk about angular and linear quantities. This is section 10.3 in your book. And let's review a little bit. I mean, what we're going to be talking about is how to relate the angular quantities we talked about last time to the linear quantities that we've been dealing with since the beginning of the year, but I think some of you were NHSing and all that sort of thing, so I want to do a little bit of a review of angular motion before. So let's talk about the angular or rotational, and we seem to use those two words interchangeably, angular and rotational motion. Okay, if I've got a blobby shape like this, an arbitrary blobby shape like this, it might rotate around a certain axis like this. If I hold it down like this, the whole paper can rotate. But we're going to talk about, rotational motion, things that spin. And we said if this is my position axis, and if I have some blobby shape, and I've got a point on our blobby shape, what I do is X, Y, and if I rotate this object, okay, this spot, okay, the Z-axis is my axis of rotation. That is, this thing is going to spin around like that. Then this is going to draw a circle, right? This location, this point, if this object is going to rotate, it's going to make a circle. So what we did is we said this was my initial angular position of this location in space. And if later on, here's my final angle, theta final. So it rotated from here over to here. So that's theta final. And so this would be delta theta, which is theta final minus theta initial. And we call that angular displacement. And then what we did last time was we said, well, it's going to take time for this object to rotate from here over to here. And if we divide by my angular displacement by that amount of time, delta theta over delta t, well, we have a name for that. It's called the average angular, am I on screen still? Barely. Angular velocity. Average because it's not instantaneous. It's averaged over a period of time. And we have a symbol for that, omega. Right? You put a little bar over it, meaning it's an average. Now, if we take the limit as delta theta goes, or as delta t goes to 0, we get instantaneous angular velocity, which we just call, so the limit as delta t goes to 0 of delta theta over delta t, well, we call that instantaneous angular velocity. And this is the Greek letter omega. It looks like a cursive W or something, but it's really not. It's a Greek letter omega. We use Greek letters to represent angular stuff. And then we said, well, what if I change my angular velocity over time? Maybe I'm going to increase the rate at which this thing rotates. Then we need an expression for angular acceleration. And we said that angular acceleration, well, the average angular acceleration is just the change in angular velocity over the change in time. If I take the limit and let delta t go to 0 of the change in angular velocity over the change in time, I get alpha, the instantaneous angular acceleration. Now, if you'll notice, that all of these angular displacement, angular velocity, angular acceleration, mathematically speaking, there's no difference between what we're doing here and what we did when we defined displacement, velocity, acceleration when it came to linear motion. And so we can, it's really just almost like it's just a variable change I've made. So all the mathematics that we did applies. And so what we said was that there, we have 4 kinematic equations. What if alpha equals a constant? What if we have constant angular acceleration? Well, if that's true, what did we say if we have if a is a constant? Let's just do this. If acceleration is a constant, you can say v equals v naught plus at. But if your angular acceleration is constant, you can just say the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. Now time is just time. But these are what are called analogous variables. We talked about that last time. And then we have delta, I'll just call it delta x equals v naught plus v over 2 times time. So this would be delta theta is equal to omega naught plus omega over 2 times time. Then we had delta x equals v naught t plus 1/2 a t squared. So delta theta equals omega naught t plus 1/2 alpha t squared. Okay, which is good. And then we had v squared equals v naught squared plus 2a delta x. That's for linear motion. Well, for rotational motion or for angular motion, we can say the angular velocity squared equals this. So basically, these are called analogous variables. So these equations that we used for situations where the acceleration is constant, we developed 4 kinematic equations to help us solve problems involving constant acceleration, constant force. Well, the mathematics is identical. Okay, so that's basically kind of what we talked about last time and how to solve angular velocity problems. Now, but if I have a rotating object, if I take this little piece of cardboard here and I hold it fixed right here, let's make this the axis of rotation, and let's put a little point on here. If I hold this down with my pencil and spin this thing around, okay, notice that this little spot, it is moving. It has a linear velocity at a certain instant in time, right? It has an angular velocity, but it also has a linear velocity. Now let's draw a line between this axis of rotation. You can just watch this right now. Now, look, as I move this thing around in a circle, notice that how fast this is moving depends on how far away it is from my axis of rotation. They have the same. Let's look at this point. We'll call this P1 and this P2. If I hold this down, which one is moving faster in terms of its linear speed? P2. P2 is a lot farther away. Now they have the same angular velocity, don't they? They're rotating. If I go like 1001, okay, they both rotated through the same angle in the same amount of time. So the angular velocity is the same, but the linear velocity is a lot different. P2 moves a lot faster than P1 does because it's farther away from the axis of rotation. I think you can see that. All right, so what we want to do is relate the linear speeds to the angular velocities, and so that's what we're going to do right now. And it's pretty easy, actually. So here's my little blobby shape. Here's the axis. We're holding it fixed right here. It has to rotate about this point. And let's look at some point over here. And we're going to go through, so it's going to rotate from here over to here in a certain amount of time. So we'd like to know, okay, what is this velocity? Well, actually, let's take a look at its displacement. If this is r initial, and this is r final. This is delta r right here. Can we relate delta r to my angular displacement, delta theta? Here's delta theta. Well, sort of. We have here, there's a slight difference between delta r and the distance I travel, right? Because this is a circle, but delta r is straight. So let's talk about, and here we really need to use radians. I mean, what's the definition of a radian? Yeah. Well, I mean, if we're in radian, what we do to calculate how many radians something is we take what we call S over R. Now, what is S?
Oh, S is the arc length of that little thing.
Yeah, S is the arc length. Exactly. And R is just the radius. So, so if I have a delta theta right here, this S can be thought of as delta R if the angle is really small. Okay? And so, you know, and that's kind of how we look at it. We're looking at instantaneous things here. Now, one of the things I'm going to do is to talk about instantaneous quantities here is I'm going to take the time derivative of this. Now, as this thing moves around in a circle, what stays the same with time? What doesn't change with time? Yeah, the radius, right? The angle changes with time as I rotate around. And my arc length that I've traced through, you know, it's going to change with time. But R stays the same. So I'm just going to write this as 1 over R, because that's a constant, times S. Now let's take the time derivative of this. d theta dt is equal to, well, this is a constant, so it just comes 1 over R. And this becomes ds dt. Oops, sorry. ds dt. Now, what does that mean? This is the rate at which I'm changing the arc length. Okay? Now, what is that, though? If I have a little tiny, you know, this is a little tiny chunk of time, well, here's a little tiny ds is right here. There's my ds. I divide that by dt. And what is that? If I went from here to here in a little tiny chunk of time, well, that's my speed. Now, I call it my speed, my instantaneous speed, because, or really it's the magnitude of my velocity vector, my instantaneous velocity. So I'm just going to call this my velocity. So this is angular velocity right here. My instantaneous angular velocity is equal to 1 over R times my instantaneous speed. Okay? I think that's kind of easy to see. But I'm going to rearrange this and say my speed is equal to R omega. Okay, so now I can take, by the way, I forgot. I can take this and put it in terms of S. S is equal to R theta. So the arc length that I go through is equal to R times the angle I trace it through. Here I take the time derivative of this, I get this. Now let's take the time derivative of this. What's dv dt? Now remember, this is my speed. This is the rate at which I'm changing my speed. Okay, it is, well, we're taking a look at speed here. The rate at which I change speed. Remember, we had two different kinds of acceleration. We had tangential acceleration and centripetal acceleration. If I'm changing my speed, what kind of acceleration is that? What kind of acceleration changes speed? Tangential acceleration. So if I take dv dt, R times d omega dt.
Centripetal acceleration is the rate at which you're changing direction.
I am changing direction, but if I'm changing my angular velocity, I am changing my speed, right? And if I'm changing my speed, I have tangential acceleration. Now we're going to deal with centripetal acceleration here in a minute. Okay, but so what this gives me is this. And this is where you have to be careful. This is my tangential acceleration. When I change my speed, I'm changing my tangential acceleration. Well, to take the time derivative, this is equal to r alpha. Okay. And so there you go. Now, what about angular? What about centripetal acceleration? What's the equation for centripetal or radial acceleration? A sub c equals what? Yeah, the speed squared over r. Now, but this, I can express this in terms of angular quantities. What is v? R, not w.
R omega.
Omega. Yes, that's right. Don't make me mad.
That'll be the first of many.
Yeah, I know. And some people call this fish. Okay, some people were last year they were calling no, that's not alpha, that's a fish. No, it's alpha. All right. What?
Yeah, why did you have to disclose that? Now,
I know. How foolish of me.
Now everyone will actually.
I know. I can't stand it. Okay, so we just substitute this in for my speed, r omega in for my speed, and a sub c is equal to r squared omega squared over r. And of course the r cancels, and this gives me r omega squared.
Wait, so is lowercase omega, does that look like a W?
Yeah, I mean, uppercase omega
Because
looks like this.
That looks like a horseshoe, and that's not,
I know. Okay, I'm not Greek. I don't know.
Oh, okay. I was just wondering. I was like, why don't you just do stuff like that?
I don't know. Kaylin, just, be quiet. All right. Now, so now we have a list of equations that we can use to move in between our angular quantities and our linear quantities for a fixed body that's rotating. If I want to know the arc length, that is s, how far I've rotated, I go r theta. R times theta. That's the length that I've rotated. If I've rotated an angle theta from the positive x-axis, this is how the arc length. Now it's a length, okay? It's not a displacement. It's not delta r, it's s. But, and then if I want to know my speed, and this is the one we use more commonly, we use r omega. And then we get to acceleration. Remember, there's two kinds of acceleration when you're dealing with, motion, rotational motion. You've got tangential acceleration, which is r times alpha. And then you have centripetal or radial acceleration, is r omega squared. And so these are things that you should add to your equation list and understand what all of these terms mean. And they're pretty easy to derive. Now we can combine these two accelerations. What is the overall acceleration? Well, remember, these two accelerations are perpendicular to each other, right? If I go back up to my drawing up here, let's pick another point on this object because this is all messy. If I have an angular acceleration, that means I'm going to have a tangential acceleration. I'll call it a sub t, and because I have a speed, I've got a radial or a centripetal acceleration. I keep going back and forth. What is the book using? The book is using a sub c right now, so I'll call it a sub c. Well, we have to add these two together to get the overall acceleration. And so it's just this squared plus this squared, right? So the overall acceleration is equal to the square root of the centripetal acceleration squared plus the, thank you. this is plus the tangential acceleration squared. And so that's going to be equal to, in terms of the rotational quantities, A sub c is r omega, but squared, but we're squaring this, so this is r squared omega to the fourth, good grief, to the fourth power, plus the tangential acceleration, which is r squared alpha squared. Now notice I have an r squared in both terms, so I can factor it out and take the square root of it, and so you get the acceleration is equal to r times the square root of omega squared plus alpha squared. So I can, omega to the fourth, thank you. Oops. Just testing you. All right. Omega to the.
If you want to know the direction too, you have to is add, right? If you're taking acceleration.
Well, this is the magnitude of the overall acceleration. To get the direction, you'd have to use inverse tangent and all that. Or look, you have to look at the geometry of the problem and figure it out.
If you're doing acceleration with direction, you just add tangential with. So you would add the components.
Yeah, you would just add this plus this. So I'd go a sub t plus a sub c. So my overall acceleration vector looks like that. Oh, I'm off the screen again. Sorry, a sub t plus a sub r, and there's my, and then you'd have to figure out the angle based on the problem. And okay. So anyway, zoom all the way out, and these are the equations you're going to use. There's a few example problems to do, but actually this stuff is, if you followed all this, and it's almost like a nice little vacation. You know, it's pretty easy stuff. So we'll do that.